For our next example, we are again using power series. We're going to find the solutions to y double prime minus the quantity of x plus 1 y prime minus y is equal to 0. Starting again with our familiar expressions for y prime, and y double prime, I'd like you to go ahead and flesh out the differential equation, match up exponents and indices, and come up with the recurrence relation. Then come back and we'll talk about it. I thought I'd check in with you and then we'll get the recurrence relation. We needed to distribute a negative into the x plus 1 and then also the y prime in that term. So we have two sigmas from that term, and in one of which the exponent, instead of being x to the n minus 1, since it's y prime, when it got multiplied by x, it became x to the n. Nothing else is really interesting about that substitution, so let's go on to the next line. For the y double prime term, we need our exponent to change from n minus 2 to k. So it looks like we're adding 2 to all of the expressions inside the sigma. So we have k plus 1, k plus 2, c sub k plus 2, x to the k, and that sigma, instead of starting at 2, starts at k equals 0. For the first y prime term, we already had x to the n. We just changed n to k, and everything else stays the same. For the second y prime term, the one that got multiplied by negative 1, we had x to the n minus 1. That now becomes x to the k, so cn becomes c sub k plus 1, and n becomes k plus 1. The starting index of n equals 1 now becomes k equals 0, and minus y didn't change except all of the n's became k's. We have 3 sigmas that start at 0 and 1 that starts at 1, so we needed to write down the first term of each of the ones that start at 0. That gave us 2c2 minus c1 plus c sub 0 plus the sigma that now starts at k equals 1. And inside of that, we have k plus 1 times k plus 2, c sub k plus 2, minus the quantity of k plus 1 times c sub k plus 1. And then I combined the c sub k's from two of the sigmas, and we have minus in front of the sum k plus 1 times c sub k. And all of the terms had x to the k, so that's been factored out, and the whole thing is equal to 0. We get two things from this equation. One of them is that c2 is equal to 1/2 c1 plus 1/2 c naught. The second is solving for the constant that has the largest subscript, that would be c sub k plus 2, and noting that k plus 1 divides out of all of the terms. We have our recurrence relation c sub k plus 2 is equal to 1 over k plus 2 times c sub k plus 1 plus 1 over k plus 2 times c sub k. We'll note that k starts at 1, goes on to 2, 3, etc. I'm going to start us down a path that we're not ultimately going to stay on. If k is equal to 1, then we have c sub 3 is equal to 1/3 c sub 2 plus 1/3 c sub 1. C sub 2 can be replaced by 1/2 c1 plus 1/2 c naught. That's going to result in 1/6 c1 plus 1/6 c sub 0 plus 1/3 c sub 1. Combining the c sub 1s is going to give us 2/3 c sub 1. Now what I have is c3 in terms of c1 and c sub 0. C sub 4 is going to be in terms of c sub 3 and c sub 2. But c sub 2 is in terms of c1 and c naught. C sub 3 is in terms of c1 and c naught. The bookkeeping just is kind of lousy. So rather than doing all of that, I said I was going to start us down a path that I wasn't going to stay on. Rather than doing all that, we're going to let C1 equal 0. And then we're going to let C sub 0 equal 0. You may wonder, how is that legit? We're not actually going to do it. It's just going to be a filter that we're going to use. We'll see how it goes. Let's go with k equals 1. Then we have c sub 3 is equal to 1/3 c sub 2 plus 1/3 c sub 1. But we've decided that c1 is going to be 0. So c3 is simply 1/3 c2. c2 is in terms of c1 and c0, but again, c1 is 0. And so we have that c3 is equal to 1/6 times c sub 0. I know, we're going to keep going though. K equals 2. We get c sub 4 is equal to 1/4 c sub 3 plus 1/4 c sub 2. We have c3 is 1/6 c naught, so that's going to give us 1/24 c sub 0. And c2 is just going to give us 1/2 c naught, because again, c1 is 0 right now. So that's going to give us 1/8 c naught. Adding those together is going to give us 1/6 c sub 0, and I'm going to stop there. Now let's go on to this other side where I have magically said that c naught is equal to 0. Again, it's not a permanent thing, it's just going to act as a filter, and you'll see how it plays out. We're again going to start with k equals 1. We have that c3 is equal to 1/3 c2 plus 1/3 c1. That's the same because we're using the same recurrence relation, but now we're supposing that c naught is equal to 0. So when I replace c2, I'm going to replace c2 using 1/2 c1, neglecting the 1/2 c sub 0. So that's going to give us 1/6 c sub 1 plus a 1/3 c sub 1, which adds up to 1/2 c sub 1. When k equals 2, we have c sub 4 is equal to 1/4 c3 plus 1/4 c2. Since c3 is 1/2 c1, c4 then becomes 1/8 c1 plus 1/4 c2, but c2 is 1/2 c1, so we have 1/8 c1, which adds up to 1/4 c1. Now before I put it together, I'm going to tell you how this filtering thing that I've referred to is actually working for us. Had we not filtered, remember we said that c3 was equal to, after we simplified, 1/6 c sub 0 plus 1/2 c sub 1. What we've effectively done is we've isolated all the c naught terms by calling c1 0. That's the filtering. And then when we called c0 0, we isolated all the c1 terms. And so this is a way to invoke like a split between the two sets of terms that we're going to have according to the constants. Now let's see how that split plays out. Generally, we have y equals c naught plus c1x plus c2x squared plus c3x cubed, and so on, as you know. What we have now, though, is one set of constants that ultimately depends on c sub 0, and another set of constants that ultimately depends on c sub 1. I'm going to split them appropriately. So first I'm going to write down y is equal to c sub 0 plus 1/2 c sub 0x squared. C1 is 0, so I have no c1 term here, and c2 is 1/2 c sub 0. C sub 3 is 1/6 c sub 0, and I know that's going to go with an x cubed because the subscript is 3. And we can round that out with 1/6 c sub 0 x to the 4th. I don't generally ask for 4 terms, but since I have it in front of us, I might as well write it down. Plus dot dot dot. And then we have our set of constants that ultimately reference c1. That was when c naught was equal to 0, so I'm not going to write down a c sub 0 for that one. We do have a c sub 1x. Now, how do we know we have c1x? Because our solutions look like c naught plus c1x and so on. So we have our c1x. And then For C2, we have 1/2 C1x squared, right? Because we're letting C not equal 0. C1 is present. And for C3, we're looking at 1/2 C1x cubed. And for C4, we've got 1/4 C1x to the 4th. Of course, plus ... I won't take the step of factoring out the C0 and the C1. I'll just write down that y1 is equal to all of the terms that we see that have the C0 in them. Y2 is going to be all the terms that we see that have the C1 in them, but I'm not going to write the constants because our solutions are what we would put together for the superposition solution. So y1 is equal to 1 plus 1/2 x squared plus 1/6 x cubed, and I am going to cut it off there, comma, y2 is equal to x plus 1/2 x squared plus 1/2 x cubed, and I'll cut it off there. Both of them get the plus ... Now I'd like to throw in a quick word about initial conditions. Suppose we know that y of 0 is equal to a and y prime of 0 is equal to b. Remember, that means when x is 0, y is a. If x is 0, then all the terms except for c sub 0 become 0. That will give us that c sub 0 is equal to a. What about y prime of 0 is equal to b? Well, differentiating c sub 0, it goes to 0. And then we have a c1. C1x differentiates to C1, remember. Everything else, when you differentiate it, has a factor of x in it. So if x is 0, all those terms are 0. The only thing we get is c sub 1, and that would tell us that c sub 1 is equal to b. So initial value problems, if the initial value is for x equals 0, are really easy to deal with power series.